Okay, can you see my slides? Hear me? Oh, the meeting's being
Yes.
recorded, so I'm on the record. Okay, thank you
Yes,
everyone for.
yes.
Oh, thanks everyone for coming. I'm very happy to be speaking to you today. This seems like a great seminar series, and I'll try to join more regularly after this. I'm going to be talking about a paper that came out in November with Stefan Alexander at Brown and David Spergel at CCA, formerly Princeton, about this new idea that we're calling Stump dark matter. This is a general idea, and an explicit sort of concrete model is dark QCD in the regime where you're looking at baryon masses that have sub EV. Baryons with sub EV masses. We call this ultralight dark QCD. So I think this sort of complements, I believe, Yu-Dai, your talk was touching upon dark QCD. So it's sort of building one complete framework for thinking about how does dark QCD fit in as a dark matter scenario more generally. And so let me mention this STUMP, stands for strongly interacting milli-charged particles. And this was fun. I mean, it's neat and sort of an honor to be doing a self-interacting dark matter paper with David, who invented self-interacting dark matter. And let me also mention, part of the reason why I'm happy to speak about this is I had a mentorship meeting last week with a sort of an elder statesman of cosmology, and his advice to me was to work on what makes your heart beat faster. And this is definitely a project, an idea that makes my heart beat faster. So without further ado, let me get started. So I mentioned this idea of a stump. It stands for strongly interacting milli-charged particles. And the explicit model that I'm going to spend most of my time talking about is ultralight dark QCD. And as a short outline here, I'll try not to go over time. You can see I only have 14 slides, so I should be able to do that. One, I want to talk a prelude, which is sort of the star of the show, which is about thinking of dense quark matter, sort of what people usually associate with what might be happening inside neutron stars, but in the context of dark QCD. And in particular, I want to talk about this regime of dark QCD, which is relatively unexplored, and how this ties into baryogenesis and cogenesis of dark matter and visible matter. And then what I want to talk about is sort of the obvious reason why something like this could never work. The idea of ultralight dark QCD, which is the Tremaine gun bound, which forbids ultralight fermion dark matter. And so how this type of model actually evades and it circumvents the Tremaine gun bound in a sort of interesting, one person said to me, obvious way. And this makes this loophole to the Tremaine gun bound makes a prediction, and that's that you should have cores in dark matter halos. And I'll finish up with some observables, which actually, so this is distinguished from both regular self-interacting dark matter models and other ultralight dark matter models like fuzzy dark matter or just axion-like particles. And I also mentioned that part of the motivation and inspiration for me working on this is fuzzy dark matter, which is sort of thinking about what could be the state of matter that is that we find this dark matter candidate. In the sense that fuzzy dark matter is a particle, but it acts like a wave. Crazy things can happen. What type of other phenomena could we find in the universe like that? So as I mentioned, the main player in the game here that's going to be inside of the star of the show, and I want to emphasize it right off the bat in case I end up being rushed for time, this idea that is the phase diagram of QCD and thinking about how this might play out in a dark sector. So here on the left, I have a phase diagram of QCD taken from a white paper, and on the right is my artist rendering of this. And the idea is that at large chemical potential, so that's a proxy for the density, and in particular, densities above the mass of the lightest baryon, which is a proxy for the QCD scale. You can have a condensate phase, different from the chiral condensate that is the hadronic phase, but here a quark-quark condensate, which is itself a superconductor. And this is the type of crazy physics that is conjectured to be going on inside of neutron stars. The neutron stars being the only place in the universe where we think that baryonic matter gets dense enough and at a relatively low temperature that you could form this phase of matter. And there's some very nice work on this by Frank Wilczek and collaborators, in particular this review gives it the name, which I think is nice, the condensed matter physics of QCD. And in particular, just based off the title of this, you can sort of intuit that the time is ripe for thinking about cosmological context for this. You know, in recent years, we've had things like ultralight axions forming DECs, superfluids, these things. So this sort of falls under that broader paradigm. But here, what's really driving the formation of this condensate is the strong interactions that you have on small scales of the hadron. And the main question that we're pursuing here is, what if nuclear density, so the density that we have that you need inside neutron stars to trigger this formation of the condensate, what if that is cosmological? Which is to say, what if in, say, the high density regions inside of dwarf galaxies, where we think there might be a core instead of a cusp, what if those regions are at nuclear density such that you could be forming a condensate? And the basic numerology here is if the baryon mass is less than about 0.1 eV, so sub-eV dark baryon masses, which is to say a dark QCD where the QCD scale is sub-eV. Then in the inner regions of dwarf galaxies, you could be forming this type of condensate. So in the title of the paper is in retrospect way too long. The title of the paper includes in it, it says Stump neutron stars as dark matter halos. And this is the idea that the stump will form state of matter analogous to a neutron star. And this could be realized in the interior regions of dark matter halos, in particular to give you cores of dwarf galaxies. And a broader sort of, one of the starting points and motivation for this was thinking about baryogenesis and new ideas for baryogenesis. And my understanding is that most of the audience here is an expert in DSM physics, so this probably needs no introduction. But let me give a 2 bullet point or 1 bullet point summary here. Is just that we have a matter-antimatter asymmetry. That's why all your friends are made of matter and none of them of antimatter. And one thing we know for sure is that the CP violation of the standard model is not enough to explain this. And this is explained in a nice amount of detail by Mark Trodden in his article from 1998. And one of the things that this has been like sort of a guiding principle for thinking about dark matter, which is the minor coincidence known since the WMAP days, now measured to extremely nice precision by Planck, but the dark matter density is about the same as the baryon density. You know, for a high energy theorist, 5 is equal to 1. So why is this an order 1 number? And the framework of asymmetric dark matter is to take this as a hint and say maybe the reason why there's baryons and not antibaryons is the same reason why there's dark matter and not no dark matter. That you could have equal and opposite, or not even necessarily opposite, but equal asymmetries in the visible and dark matter. So a question that we were asking is, well, what if the lightest stable state, not even necessarily that dark matter just consists of one state, but what if the lightest stable state of dark matter is milli-charged under B? So this idea of milli-charged particles has grown to prominence in the context of thinking about a small electric charge for dark matter. But actually, you can think of models where, and I'll show one in a second, it's relatively straightforward, to build models where dark matter is milli-charged under global symmetries of the standard model, such as baryon numbers. Okay, now if we just take the paradigm of this asymmetric dark matter, where we have a cogenesis of dark visible asymmetries, the implication of milli-charged V and the fact that you have about the same amount of density in both dark and visible matter tells you that the dark matter must be ultralight, such that you have this astronomical number density in order to get the right asymmetry. So what the type of model this suggests is an ultralight dark baryon, which is to say, there's some nice papers which tie in take this asymmetry and then you can tie in the dark QCD scale and the visible QCD scale. Here, what we're saying is that there's a hierarchy between the dark and visible QCD scales. And this is essentially set by the charge, the baryon charge of the dark matter. So I don't want to go into too much detail here, but just to show one sort of a model building framework for how you can get part of dark matter that is milli charged under baryon number. And this sort of general recipe can work for any global symmetry of the standard model, but in particular, what we're interested in here is dark QCD. So in particular, something that is milli charged under baryon number. And here we're putting together two things. One is the idea that you can have gauged U1 baryon number in a way that's totally consistent with proton decay constraints, but does actually introduce new particles that you could potentially observe at the LHC and things. And that was the motivation for a series of papers around 2013, 2011, this very nice PRL, where they put forward the sort of very simple idea that if the Higgs, which is Higgsing baryon number, is itself has an integer baryon number charge, then so here's just a simple scenario where B, this is a field strength tensor of baryon number, and S is some new Higgs field. If the S has integer baryon number charge, the only way that I can communicate baryon number, the fact that baryon number is violated, is through higher order operators. So for example, if S is baryon number charge 3, then I need the operator which would couple S to quarks has necessarily S times 9, or you need an even number, but to put 2 S's and 18 quarks, or you can toss an electron in there rather. They talk about this idea in that paper, but so the simple way to get gauged U1B in a manner completely consistent with all experiments is that the field that's Higgsing B has integer baryon number charge. And so at low energies, you have an approximate global symmetry, approximate in the sense that baryon number is only violated by irrelevant operators. And as explained very nicely actually in a very recent paper, you can easily cancel of course, the starting point for this is you need to cancel the standard model anomalies for U1 baryon number. And you can do this by tossing in 4 new fermions with specific charge assignment. So part 2 of the puzzle for us is 1, we're thinking of a gauged U1 baryon number, but 2, then this general recipe, which I think the first paper on this was in 1986, this PLB by Hold'em, is the idea that if you have some dark U1 and a visible U1, and you have this kinetic coupling between them, this endows the dark matter particle with, usually we're thinking with the visible U1 is electromagnetism, this would give the dark matter particle a small electric charge. So here, the dark U1 could be a U1 baryon number, so dark matter gets a small baryon number charge. So if you have some coupling, which is epsilon over 2, the field strength tensors, the dark matter particle gets baryon number charge epsilon over 3. One third being the baryon number contained by a single quark. So all of this to say, it's actually pretty straightforward to build models that are merely charged under B. And I think actually that is a sort of an orthogonal independent direction for future work, particularly given the very nice work. I saw Seth is in the audience. He's done some very nice work on dark matter baryon interactions. So there's a number of papers on this, which I think this in itself is sort of a interesting portal for looking at dark matter baryon interactions. There we go. So now I want to come to the obvious, well, I mean, depending who you are, I don't mean to be condescending by calling it obvious, but there is a well-known reason why ultralight dark baryons could not conceivably be a reasonable dark matter model. And this usually goes by the name, the Tremaine unbound. And the simplest and most intuitive explanation actually came 30 years after the Tremaine gun paper, and it's just essentially based on the Pauli exclusion principle, which is that the most densely you can pack fermions into phase space is just filling up a Fermi sphere. All right, so every new fermion I want to toss into this small region of space has to have higher and higher momentum. And I know if I have a heavy object, I have a lot of particles, and necessarily then, because of the Pauli exclusion principle, I am tossing in new particles with high momentum. So at a certain point, when I toss in a new particle, its momentum will be such that it's more than the escape velocity of this compact object. So there's a limit to how heavy can an object be when I start tossing in ultralight particles. And this translates indeed to a lower bound on a fermionic dark matter candidate. Excuse me, once you make a small number of assumptions, that is, it needs to be greater than 100 electron volts. Now, the original incarnation of this is slightly more sophisticated, a bit more slick, but actually is less robust in that it has to make some assumptions. But, and this is your original argument by Tremaine and Gunn, which applies the Louisville theorem to the distribution function. And in particular, if you just assume that at early times you have a Fermi-Dirac distribution, and at late times you end up with some isothermal halo, and you say, I have collisionless cold dark matter, so there's no collisions of dissipation, then moments of the distribution function are conserved. And in particular, one conservation theorem that the maximum of the distribution is conserved. And from this, you can find out, just to get the right density and total mass of the halo, a lower bound on the dark matter mass, which is incidentally, up to a factor of 2. There's like, well, it's actually like a 120 or something, depending on the galaxy. This gives the same, the order of magnitude of the bound is the same as the Pauli exclusion principle, which is what I mean. So both of these independent arguments tell you non-interacting cold fermions, the lower mass bound is about 100 electron volts. But now let's return to QCD. And whenever I say QCD in this talk, what I mean is dark QCD, and thinking about the high density regime. And so the article that I found most useful, if you're interested in looking into this, is by these authors, this Review of Modern Physics in 2008. And there's a pretty huge literature on this, and it's a neutron star community has also worked on this in a lot of detail. And maybe there's one in the audience who's from that community that you can maybe give you more references from their side. So I'm coming more from just the quantum field theory side of things. And the general picture is that when the number density, your density to the 1/3, so an energy scale is greater than the mass of the lightest baryon in theory, which is roughly the dark QCD scale, there's a VEV for this quark-quark bilinear. And in particular, so I'm writing in all the indices here, which is maybe not super important for the moment. All I want to emphasize is that you get a VEV here with a delta here is in condensed matter language, you say this is the order parameter for the phase of the theory. When this VEV is non-zero, you're in the condensate phase. And I should mention, this is the Higgs mechanism in disguise. Maybe that's another story, a historical detour involving Nambu. And the key details for us is that similar to the hadronic phase, when you're forming quark-antiquark VEV condensate, this breaks some of the symmetries of the theory, and this dictates what is the low energy effective field theory of that phase. And so in this context, you're breaking both color and flavor symmetries to a combination of color and flavor. So just we call it color flavor symmetry. And this goes by the name color flavor locking. And what this is, and this isn't just an analogy, there's some truth to the statement. This is a QCD version of BCS, the BCS theory of superconductivity. And so here what you have is a color superconductor, which is to say, so the field theory definition of BCS theory, superfluidity is the breaking of a global U1, and superconductivity is the breaking of a local U1. And here we're breaking the local SU3. So the charge is color charge, and where a superconductor just in the exact same sense that BCS is superconductor. So one of the essential ingredients to get phenomena like superconductivity is the presence of an attractive interaction. So surprisingly, the QCD version is simpler than the QED version, which is almost never the case. And the reason for that is because you have an attractive interaction at tree level, just quark-quark scattering. And how you can see this is Corcoran scattering evaluating some trace over the SU3 matrices. And this gives you some delta functions, and I can get this to be positive in some region, which indicates you're getting this scattering generates an attractive interaction. And in particular, I couldn't remember who to attribute this as a quote to, so I removed the quotes, but I've seen it before. I think it was maybe Frank Wilczek, but it said anti-symmetry is attractive. If your nose is crooked and you are anti-symmetric, you can keep in mind that anti-symmetry is attractive, and this is maybe what's driving the dark universe. So what's happening here in complete analogy with BCS theory is they're forming Cooper pairs of quarks, and you can actually calculate, and the calculation is contained in this review article, how to calculate the VEV of the gap. So this is the Higgs VEV in this model, and it's determined by the density and the coupling that you calculate through RG flow, for example. And again, the context in which we're thinking about this right now is that you have some sub-EV QCD scale. So this, I would think, is set in at sub-EV scales. And as a quick plug, let me mention that I think it was the first time this type of phenomenon was talked about in a cosmological context was an earlier paper that I wrote with David and Stepan talking about thinking about SU2 and how some sort of SU2 condensate phase can be connected to particle production during inflation. So now let's come back to the Tremaine-Gunn bound and think about how does Tremaine-Gunn face off against BCS theory and so superconductivity. And actually, it gets around it in a pretty nice and slick way. And this is what somebody accused me of the article being obvious, and so obvious as to be not worth writing. But the basic premise of Cooper pairing is that you take a fermion with momentum k, and it pairs up with a fermion of momentum minus k to make a scalar. So the fermions are bosonizing. And the neat thing here is that the Pauli exclusion principle is always obeyed, but by construction, you're forming these bosons in a zero momentum state, so that they're not flying away. There is no escape velocity bound because you're tying these high velocity fermions into zero velocity boson. Now, if you come to the Louisville theorem, but these strong interactions that are driving Cooper pairing gives you both collisions, and actually in the QCD theory, because you can Bremsstrahlung away a pion, you also have dissipation. So in fact, you don't have these conservation laws, and the final configuration of what does a halo look like, you have to solve the equations for hydrostatic equilibrium, and you have some equations of state that governs the fluid in this phase, and you can go to the neutron star or QCD literature for what is the equation of state of dense quark matter. So the first claim of this paper, which I think is interesting, is that ultralight dark QCD is a loophole to the Tremaine-Gunn bound. So I don't have a ton of time left. I want to wrap up before 9:30. So maybe just let me mention that there is a known equation of state of dense quark matter, and you can parameterize it with there's a single parameter which tells you what's the dominant effect. Is it the effects of Cooper pairing versus just a degenerate Fermi gas and non-interacting particles. And let me come to the exciting bit, which is that you can take the TOV equations for hydrostatic equilibrium and the equation of state and ask what types of solutions can I find here. And what was exciting is that you can find solutions which correspond to constant density cores. And in particular, you can get dark matter cores which have about the size and the density that we observe in dwarf galaxies. And for example, this is looking at the pressure profile, and the procedure when you're looking at the TOV equations is to say the solution truncates when the pressure hits zero. So you have, and I include this, the plot, this is the dimensionless dark matter density, which is not super informative other than the density truncates at a certain finite radius. And so we have an extremely close to constant density core with sizes and densities that we actually observe in dwarf galaxies. So this is exciting that a loophole to the Tremaine gunbound makes a prediction that and the basic premise of the loophole is that you should form some condensate phase in high density regimes, and it is in complete analogy to what is happening in a neutron star. So the idea here is that the cores of dark matter halos, so a dark matter core is itself a stump neutron star, which is to say there's a central region which is in the superconducting phase of the dark QCD theory. And there's other interesting phenomena which can happen. So for example, there's a beautiful paper by Yi Ming here, I think is in the audience, and collaborators, Sam McDermott at Fermilab, which is published in PRL, about looking at dissipative dark matter models, and models where you have both the self-interaction and so you have scatterings and dissipation. And in particular, one phenomena you can have in this dark QCD theory is you naturally have a coupling of the nucleon or baryon to pions. And so if your dark matter is in the, just as how an electron can radiate away a photon, dark baryon can radiate away a pion. And if you look through their paper and you sort of follow their procedure, the general intuition that you mentioned is, maybe for the moment, don't pay too much attention to the formulas, except for you have here new loss is roughly the energy loss per dissipation event. And you have an exponential suppression, which corresponds to essentially if the energy loss per event is too high, then you need a very high energy particle to undergo to give up any energy. So the event is too rare to have any impact. And then if the energy loss per dissipation event goes to 0, then there's no energy dissipated at all. And so in the context of self-interacting dark matter, where the eventual fate of dark matter halos and the cores is to undergo gravithermal collapse. So here, of course, this requires some explicit numerical studies, but we conjecture that the stumps should be safe from gravithermal collapse due to the fact that the whole premise of the whole existence of the core is premised on there being some non-zero pressure in the central region, which should prevent it from collapse. But in any case, the limits on cooling, if you just ask what region of parameter space would have significant cooling, and let's just demand we're outside of that region, corresponds to, you can write it as a ratio of the quark mass to the QCD scale. Only a small region of it is ruled out if you demand that there not be significant cooling, which in the context of usual self-interact dark matter leads to gravithermal collapse. And so here, the fundamental constituent, remember the mass of a baryon is driven mostly by the binding energy of the baryon. And so here what you're ruling out is a few orders of magnitude of the quark mass. There's other really cool things that can happen, such as there's a correction to dynamic friction as a superconducting core is passing. So you have a satellite galaxy is falling into a halo, which, from the Gaia results is one of the super exciting things that happened in the last couple of years. We know happened in the recent history of our Milky Way galaxy. And sorry, so I'm very much out of time. Let me mention that there is cool condensed matter stuff which can happen. One of the most well-known condensed matter things is called invariant reflection, dates back in the 60s. And the basic premise is that if a charged particle enters a superconductor with energy less than the gap, by definition, the word gap means it cannot exist in the superconductor. And what actually happens is that you spontaneously nucleate a Cooper pair, and the superconductor shoots out a hole, which is in this case just an antiparticle. And also let me mention that there's some really neat differences between stumps and ultralight scalars, just by virtue of the fact that one is a fermion and one is a boson. So they have different effective actions with different interactions. And I think also the fact that it's superconducting, there can be crazy things like in mergers of galaxies, there's a angular momentum exchange. And whenever you have angular momentum, you can in a VEC or superconducting uniform vortices. So one prediction, that this of course requires detailed study, but is that you could have in a galaxy merger the spontaneous nucleation of superconducting vortices in the host halo. So now let me close, and I'm 1 minute over, right? I think that's okay. Is what I've been talking about today is this idea of Stump dark matter. And Stump here, in the tradition of abusing acronyms and forcing acronyms, it stands for a strongly interacting ultralight really charged particle. And the story is one, that there is a loophole to the Tremaine gun bound, which rules out ultralight fermions, and the loophole is that in the region where you think you need the most fermions, actually they're behaving like bosons. And the class of models which can do the job is Stump. And one concrete model which has interesting observables is ultralight dark QCD. And so a general prediction of 1 and 2 here is that you should have dark matter cores. And this is in the context of ultralight dark QCD. It's in close analogy with what we think might be happening in neutron stars. And I think there's some neat next steps. One, just in this model, but more generally, cosmological signatures of particles which are really charged under B. And what this does is it tells you what are the interactions that you can have in the effective field theory. 2, in context of dark QCD theories, there's a possibility of having a cosmic pion background of these ultralight pions, which is incidentally just today, there's a paper right on that cosmic axion background. 3, something I didn't touch upon at all here, but is definitely worth looking at, is actual concrete models of baryogenesis, which can work in the ultralight regime. And 4, I think thinking about things like vortices in particular, this model is distinguished by superconducting vortices, will be really neat. So thanks for coming.
Yeah, thank you very much. So we have some time for questions.
I have a question. So it seems to me that here the story is basically the same phenomenon as the modification to the equation of state of a neutron star because of QCD. Basically, I'm talking about the correction to the TOV bound that happens in a neutron stars because of the stiffening of the equation of state. Now, there the Oppenheimer bound is changed by an order 1 number. My question is that, do you have an intuition why the same thing here instead changes it by 3 orders of magnitude?
Right, so you're saying going from a degenerate from a gas to a...
yeah, it's the same calculation,
yeah,
basically. The Riemann bound or the TOV bound is the same thing, basically.
Yeah, yeah. So here I'm doing whatever I please with the parameters, and for example, be effective. So what I would say is that in the QCD context, you are bounded in what you think can be the reasonable parameters, versus here, it's just a different region of parameter space. But I don't have an intuitive answer to that at all. And maybe that's just something that's definitely interesting to look into.
Okay.
But in fact, I have a related question. So if the coupling, the effective coupling that appears in your formula is perturbative, so would you still say that you evade the Tremaine-Gann bound by a large amount?
Sure. If the which effective coupling?
So you have this gap that depends on the...
Yeah.
So for example, if the mass is less than 0.1 electron volt, the system is essentially perturbative. So would you still say that you evade the Tremaine-Gann bound?
Why is the system perturbative if the mass is less than?
If the density is bigger than lambda QCD to the 4th, lambda dark to the 4th, then you have...
I mean, it's not necessarily weakly coupled, right? You can have...
It is literally weakly coupled. I mean, this formula contains a weak coupling.
Yeah, so this formula here is at weak coupling, and you can do like one approach to studying this is at weak coupling, but it's not necessarily weakly coupled. But we don't know if the interior of neutron stars is weakly coupled or not, for example, too. Right. So there's no, and also in the fact that we don't have any measurement of the strong coupling.
That the Tremaine-Gann bound disappears is also weak coupling.
it can be weak coupling, but it doesn't need to be. Is my answer.
So if G is arbitrarily small, you will still say that.
Oh, I see what you're saying. So if in the limit that the gap goes to 0, so there is, so the, and then you're saying in the limit that delta goes to 0.
I mean, it's related to Daniele's question. In the strong couple regime, it seems difficult, but in a weak couple regime.
Yeah, I mean, that's a good question. Thinking about the limit that G goes to 0, and you're saying that if more generally the limit that delta goes to 0, the gap, can you still evade the Tremaine-Gum boundary? That's it.
In the formulas at some point.
Yeah, that's a good question, and I'll have to think about that more.
Do we have more questions? So maybe we can move to next talk. Thank you.
Thanks, everyone.
Yep, let me try to share the slides. Is it good? Hold on. Also, can you hear me okay?
Yes.
Yeah, sorry.
Not now.
Oh, okay. Sorry. Let me start again. Okay. Yeah. Should I start or yeah? Either way.
Yes, please start.
Yeah. Hi everyone. My name is Yu-Dai Tsai. So today I'm going to talk about resonant self-interacting dark meson and small-scale structure. And most of you don't know me, so just a brief saying that there's a lot of different things I work on. And today I will focus on the new dark matter models that could give us a lot of interesting signatures and observations. And I also work on accelerator probes, proposing new experiment to probe, for example, midi-charged particle, and also high-energy neutrino physics at LHC. So there's a lot of interesting things to be done. And kind of connects to what Evan was talking about. I also work on actually the neutron star, but not the new kind of neutron star, but the actual neutron star, and question some of these well-known merger. Are they really neutron star merger or not? Because it's actually not true that they have to be neutron star merger. They could be neutron star black hole merger. So if you're interested in the astrophysical thing, we can also, or the accelerator thing, we can also chat afterward. But today, the main topic would be to go back in time and try to understand the meson structure and apply that to dark matter. So as you can see from this plot on the left-hand side, this is a plot made by my kind of ancestor or people that are very established, and they work out the meson spectrum. Actually, they're also at Fermi Lab in Chicago, so I actually learned a lot from them. So they study the quarkonium level spacing and use that to understand the meson spectrum and the relation. And 43 years later, we use the almost exact same formula to calculate the dark meson spectrum. So my talk, in some sense, would be much simpler that compared to the Evan's very clever idea. For us, most of the things that I'm going to talk about directly have a standard model analogy. So it's very interesting to look back into standard model to see what we can learn from there. Good. So here's the outline of the talk. First, I'll give you introduction, and then I'll talk about the light quark dark kaon model. Then I'll give the heavy quark asymmetric dark matter model. And if I have some time, I'll talk about this kind of SIMP and Elder model and with lattice results. But I might not have time to go over the last part, but I will definitely mention the first two parts. Okay, so why do I study potential dark matter solution to small scale structure problems? I'll mention what are these problems and give one example, but it's kind of very interesting to think about this for the following reason that we'll study. And potentially our model could also help address part of the H0 tension, but that's still under construction. We're still working on that. So for the small scale structure, meaning of the small scale structure is that you measure or you look at this galaxy or cluster, they are smaller scale compared to the cosmological scale that are much bigger, right? So small scale structure, there's several of these problems. They are presented in the past, and I'll explain the first one. But the other ones are kind of related, but also in different aspects when you look at this galaxy or cluster. So I will mention what is core versus cusp, but the other ones that we can chat afterward. And these were used to be kind of a big problem, but recently there's a lot of study that have the baryonic feedback or supernova to help resolve these issues. So maybe you don't have to necessarily think about them as problems, but still it's very interesting to look into them, as the reason I will explain in the following slides. So let's look at the easiest one, that is the core versus cusp problem. So if you look at one of the galaxy, they are more dark matter dominant. For example, this DDO 154 galaxy. This is just a small galaxy, and DDO has nothing to do with physics. It's just a David Dunlop observatory. So if you look at astrophysical naming, sometimes it just doesn't have any physical meaning. So DDO is this galaxy, and now you look at the circular velocity of the hydrogen, neutral hydrogen around the galaxy. Then you can get all these data points, black data points. Now I say that, okay, so this is dark matter. So we know exactly what to do. We translate the circular velocities. So of course, first we feed the data, and then we translate these to the profile. And what you find out is that, so the red one is clearly a better fit. So the red one give you a kind of like a core profile. Core means that it's not very cuspy. These is not very going up sharply. But if you do a dark matter simulation, cold dark matter simulation, then it gives you a cusp. So cuspy kind of profile. So it means that the cold dark matter may not be a good explanation or a good thing for this galaxy. So there was this thing that people were confused about. Of course, then people can say, oh, maybe I can turn on a supernova that can blow things away in the center. So then you can resolve the core. And that's a possibility. But you kind of turn your knots for different galaxy. And they also come up with a more sophisticated simulation. So there's a lot of things going on right now. So this might not be a real big problem, but it's something that is intriguing and could help us understand the nature of dark matter. And if you're interested, there's a review by Xiang and Haibo. They are very comprehensive. But yeah. Okay, so I certainly don't necessarily treat small scale structures as problem. Rather, they are really opportunities, because we really don't know the nature of dark matter, even though we have a lot of speculation. We really know next to nothing about it. And small scale structure is a way to at least set the constraint for dark matter self-interacting. So even if you don't really care about dark matter, even if you don't believe in dark matter problem, small scale structure problem, it's still a great way to set constraint, as I will explain very soon. So by looking at the galaxy and cluster, you might be able to refer the dark matter self-interaction, or at the very least set the constraint. And also, it's not a trivial constraint. But the introduction of final slides, also these interesting phenomena, these self-interacting dark matter phenomena, happens when the dark matter is around MeV to GeV. And this is kind of, so you can say, okay, there's so many different kind of dark matter candidates, you can work on whatever you want. So why do you care about MeV to GeV? So my argument is always MeV to GeV, there's several interesting things. First, you can have the thermal dark matter. And also there's a lot of anomalies. And I know a lot of us are interested in anomalies. I look up the audience. So I believe that new physics always first come from anomalies. Of course, most anomalies are systematic errors, but new physics has to come from anomalies. So you have to see somewhere that the standard model of physics start to crack. So then you can discover new physics. So I think it's very meaningful to look at problems or anomalies to start to unveil the actual story behind these anomalies. Okay, self-interacting dark matter, velocity dependence and similarity to standard model. Okay, So as we already heard, David Spielberg and Steinhardt, in 1999, they have the self-inheriting dark matter idea to resolve the kind of core versus curse problem. And I will explain a little bit more how they do that. But one observation without doing anything. So before we do anything, first thing we should notice is that the dwarf galaxy and cluster have a very big difference in their scale. And as a result, the relative velocity is also very different. So there is like 2 orders of magnitude in terms of the kilometer per second. So now the interesting thing would be asking if the self-interaction is really interesting. Should it be velocity dependent? And the answer is yes. So there is this very nice paper. This is a semi-analytical analysis of the different galaxy and their preferred self-inheriting cross-section divided by m. Okay, so by the way, so one thing first we should notice is this on the y-axis is sigma times v and thermal average. So there's a v built into it. So if you want a constant cross-section, it's actually going like this, this line that goes up. So you can clearly see that this data, you cannot have a constant cross-section to fit it. You need a dropping, you need a 1 over v kind of cross-section to fit this kind of cross-section at least, or 1 over v squared, 1 over v to the 4th, depending on the model. But you cannot just have a constant cross-section. So that's the first thing. And forget about this gray data. These are just simulation. This is sometimes confusing, so forget about this gray data. So the red one is dwarf, so it's very small. The blue one is low surface brightness, galaxies, and the green one is the cluster, so much bigger scale. So how do they do this? So the idea is kind of very simple. So you say, I have a rate times times is how many times I have the dark matter interaction. So you require it to be 1 time. And then because of that, you can fix the radius. So within a small enough radius, the dark matter, I consider it to interact 1 time when I provide my cross-section times V, thermal average divided by M. So when I provide this parameter, then I can determine the R1. And the R1, once you determine it, inside it, you can solve the isothermal equation. Outside of it, you just use NFW, meaning that you assume outside of it, it's almost like a cold dark matter. So now once you go through this practice, you feed this profile back to the 3 different type of galaxy or many different data. And that's how they get this sigma V over M. So it's very nice and kind of semi-analytic. So it's very cool. And it's something that, and then because of that, they find out that, okay, so the preferred model is this model. You have a 50 GeV dark matter and 70 GeV, 17 MeV gauge boson, and they can also link this to another anomaly. There's a lot of interesting story here, and I know Yiming and other people work a lot about this on this as well. But I want to study a different type of model that is not really having this light mediator, because you can always ask, why do you have a light mediator? It doesn't. You could build a more complicated model, but I want to just consider nuclear physics. So you have a so if you look at this cross section, it's very close to, for example, NP to NP elastic scattering. I mean, it could be coincidence, but as I said, it could be telling us something that maybe there's analogous to standard model. So could this be from a QCD like dark matter? And that's something that we want to find out. Okay, so resonant self-interacting dark matter. So now I not only want to have self-interaction, I also want to have velocity dependence in the right position, right? I want to have this kind of velocity dependence. So then one of the models that I consider, and many people consider, this one, Hitoshi also considered this previously, is you have a dark matter that goes through a resonance and then come back to the dark matter. So this is a S-wave channel. So mass of the resonance has to be about 2 times of the dark matter mass. So you can go on a resonance, you can go on the Bragg-Wigner resonance or the mass resonance and come back. So then you can have enhanced cross-section in a certain velocity. So that's just a very simple toy model, has nothing to do with Meson. Okay, so just a few words about this. So this is very interesting. This is worked out by this paper that so you could have this kind of a resonance and you work out everything. So when you have a kinetic energy matching the mass difference between the resonance and the two dark matter states, you could have a resonance. And because of that, you could have this kind of peak that fits the data pretty well. So here they're considering kind of like a P wave. And this is also what we use. So they consider kind of like a P wave, but resonant kind of self-interacting dark matter. So the reason why it's P wave is because they use a vector resonance. So once you look at this, you say, oh, this is standard model, because in standard model, you have K plus K minus go to phi, go back to K plus K minus. So K is SU bar or US bar, and phi is SS bar. So you can just go through this resonance and come back, and you actually have the resonance. So this is very cool. So now we can look at a lot of resonance. So the easiest one, simplest one are, for example, K plus K minus, they can go to phi, SS bar, or B0 that you have BB, and then you can go to this upsilon 4S. So there's many of these very interesting resonance, and actually many of them. So let's actually have a quick review of all the different kind of resonance. So in this plot, we're not doing anything dark matter. This plot is purely standard model. So I also do some standard model physics, not really, but I organize it. So if you look at these, so in the, I also do neutrino, so I do standard model physics. Okay, so these black dots are 2 times of the pseudo scalar mass. So starting from pion, this is a pion mass, this is a kaon mass, B meson mass, and D meson mass, 2 times of them. So you can see then that they grow up like this. They grow up like this. And now you plot the vector resonance. So starting from, for example, the 3 rho, omega, and also all different kind of meson like phi or psi 3770 or upsilon 4S. I'm sure my pronunciation is not perfect, but you know the symbol are here. So you can see that it actually crosses through all these different kind of resonance. So meaning that once you go close, you're actually go near the resonance and here. And you find out that it's easier and easier to hit the resonance once you raise your quark mass. So that's very interesting. So you can go through this level. And you also see kind of why you will have a resonance, because you have many different levels and you just keep going up. So you're about to cross some of these resonance anyway. So that's kind of one explanation why there's so many resonance in standard model. But there's a lot of other resonance. For example, you have this triple alpha process, which is a mystery, because if this number, this carbon and this beryllium and alpha, if they don't arrange this way, the astrophysical process will be very much different. So there's all this very interesting process, and people come out with the anthropic principle to explain this, because if this number is not this small number, then we might not be here. So there's a lot of interesting thing just to look at the resonance. So if you're bored, you can just open a PDG and look at all the resonance and ask, why are these that? And maybe you'll be convinced that naturalness is natural. Like not being natural is natural. So that's something that we can do. Okay. So dark kaon and light quark model. So now that we understand these K plus K minus to psi, to SS bar, for example, let's build a similar model to that. So the model will be very simple. I will directly make the analogy between the dark kaon and dark psi phi or psi phi, dark phi to the phi, and I will make the coupling to be the same, for example, to be very close. That's actually, I'll make it the same. And eventually I will find out that the dark matter will have to be around 1 GeV. So I can just input all these, and then I find out that I can actually fit this. Of course, the parameter have to be specified, as I will show you. So the model is very simple. So if you actually want to write down a model, the model is that you have a U quark and S quark, but nothing more. So everything here now is dark matter. So even though I use U and S, these are dark matter. So the S quark is much heavier than U quark, but both S and U are smaller than lambda QCD. And then you can have the K plus, K minus, and K naught. But they are like pion because I only have 2 flavors. So they are like pion, but I call it K-on because the S quark is much heavier than U quark. So there's only 2 quark and 3 type of meson. And these K plus, K minus can be dark matter because they're stable. And of course, they can annihilate to K naught, but I play with the effective theory to make the K naught heavier, then they will not be dark matter. So K plus, K minus would be dark matter. There's some more detailed model building you can find in our paper. So anyway, so once I have these and I want to fit to this parameter, I have to be analogous to standard model because a lot of these couplings are not calculable. So there are 2 things I can fit to standard model. One is I fit this K plus, K minus, K plus, K minus, 4 fermion interaction, 4 K-on interaction. So if I fit these, then I find out my preferred range of the dark matter is about 100 MeV. So there will be an interesting parameter here. They give me kind of the correct self-interacting cross-section. So this is what this regime is. Sorry, where did it go? Oh yeah, this is regime 1. Regime 1 is fitting the 4 K-on interaction. And then there's a regime 2 that I fits this coupling between K plus, K minus, and phi to the standard model value. So this gamma is just a parameterizing of this G squared over 384 pi. This is just a parameterization. But I fit this G to be the same as standard model G. And it forced my mass of the dark matter to be about 1 GeV. So the perfect situation would be the 1 and 2 are the same regime, but they happen not to be the same regime. So you need to change the coupling a little bit from the standard model for them to match. But that's totally fine. I mean, it's just we cannot calculate it, so we don't know the parameter. But in reality, if you are very good at lattice QCD, then you can really directly calculate all these coupling. And I'll show you one example in the end. So these are the things. So the reason why this plot is also have a y-axis is because we also want a freeze-out scenario. So we introduce a very simple freeze-out scenario that we have K plus, K minus go through dark photon, goes to standard model particle, and that's how we find these parameters. So you could still have the freeze-out, and there's some requirement of the dark photon also to be on resonance, but that's just a complication. And now you can have the direct detection probe, all kinds of different probes for this parameter. So for these, we're just having one of the simplest out-of-the-box model for the freeze-out, but you can certainly consider much more complicated freeze-out that directly ties the QCD together. For example, you can freeze out through Xion. That's something that we're working on right now. Okay. So this is the light quark model. Now, light quark model is interesting, but not so good. So I want to have a better model that is the heavy quark and asymmetric dark matter model. So this model is where I can use the very interesting thing from the past. So this is the standard model modeling for the different meson spectrum and so the pseudo-scalar mass. So this curve is the pseudo-scalar mass, and all these levels are the vector meson mass. So as I say, years later, we also do the same thing. So let me get into it a little bit more. So now I want to actually use the heavy meson to model my dark matter. So the idea is this. So I have a B bar U. So all these are dark right now. So yeah, when I say DM here, it always means everything's dark. So now I have a B bar U kind of dark kind of meson and C U bar meson. So I have C prime quark and B prime quark, and I'll just label C and B just for simplicity. So I have 2 heavy quark, and then they are asymmetric, so they don't annihilate away. So then now I form this B prime dark matter and D prime dark matter. and their abundance is about the same because I set B and C to be the same mass. So they are the same mass, but they are asymmetric, so they won't annihilate away. So now I can have the B and D and go into some kind of the upsilon, NS kind of state, which is the combination of CB bar kind of meson. So now I can go through the resonant meson because I can have the CU bar and UB bar and go into CB bar. So that's the resonance that I'm looking at. Right, this is analogous to BB bar going to upsilon 4S. So this is the heavy quark, but inevitably you also have the light. So this is a heavy meson. Inevitably you also have the light meson that is about the same as the lambda QCD. So eventually I'll have to have this light in meson to decay away. So this thing will eventually decay away. So eventually only the B and D will be the dark matter. So that's the setup and everything will work. So then I want to go through this. So every of these single thing can be kind of calculable. So you just have to assume the log potential. So you assume that this heavy quark and light quark have this log potential, and then you can calculate all these meson spectrum. And once you calculate this meson spectrum, you find out that the heavier the quark mass, the easier you hit the resonance. So delta N over MQ is a parameter that we come up with to quantify how easy it is to hit the resonance. So this N is the level that I go through. So if I go through here, then the N will be like 9 or 10, right? So if my MQ is very heavy, much heavier than lambda, then I will go to a level of 10. So the idea is the larger the MQ over lambda, the better you can hit the resonance. And that's the intuition that we always have. So you always want to go to very heavy quark so that you can hit the resonance very easily. So it's natural to hit the resonance. So that's like simplest idea. So we want the MQ over lambda to be about at least 10. So you want a very heavy quark and a much smaller lambda QCD. Okay, so that's the story here. You want the heavy quark and light lambda QCD. And now the phenomenology, you can consider phenomenology. Now you need the pion to decay. So this again is dark pion. I have my dark pion to decay to some dark photon. And dark photon is just kinetic mixing dark photon, the most simple one, again, out of the box. You have a massive dark photon, it can decay into mu plus mu minus, for example. So this is out of the box. And now everything is almost fixed because you have the asymmetric dark matter that is 5 GeV, because asymmetric dark matter is naturally 5 GeV. So I just have the asymmetric dark matter to be 5 GeV out of the box, just the most simple model. And then my lambda is about the same as mass of the pion, and this has to be 2 times of the dark photon mass. So these actually start to fix all the parameters, because then now I can have this story. So I have MQ is about the same as the mass of the asymmetric dark matter to be 5 GeV. And this will push my lambda to be much lighter. So we'll push my lambda to be, let's say, 100 MeV. So my lambda has to be 100 MeV or lower. And my dark photon has to be even lighter. So then the better that I can probe, I can have a lighter dark photon, the better I can hit the resonance. So I want the splitting to be about 10. So that's the interesting parameter here. So let's say 500 MeV or lower would be interesting. So that's why we have this parameter. So this is just a kinetic mixing dark photon. And the lighter you can do your dark photon, the better. And there's already a lot of probe that you can do to study this dark photon. And I actually propose one of these long quest experiment. So this is good to see 2 things merge in some place. And yeah, so this is the story. And to finally summarize, oh, sorry, how many time?
5 minutes.
Okay, yeah, I can finish in 5 minutes. So just to summarize this part, like symmetric dark matter is about 5 GeV. And interestingly, if I want to fit this resonance, I found out my G of the BD gamma, BD upsilon for S, sorry, this is upsilon. BD upsilon for S, the coupling between the pseudoscalar Meson and vector Meson is about 27 if you use dimensionless coupling. And the standard model value is actually 25, so it's very close. So this is a very interesting and exciting coincidence. And I just need my dark photon mass to be about 100 MeV. And there is all these interesting parameter space you can probe. And the kinetic mixing, of course, is this parameter. So if you have all these things, then you can both have a nice asymmetric dark matter story and a nice resonant self-interaction. Okay, so this is the asymmetric dark matter part. So I do have a few minutes. I can mention the Sim and Elder model if you're interested. So Sim and Elder are just names of this interesting model. That Sim just means that you have strongly self-interaction, so the dark matter is freezed out to 3-to-2 self-interaction. And if it's certainly a little bit complicated, and we can chat afterward about this. And an Elder is just something that first elastically decouple, so elastically decouple relic, first elastic decouple, and then 3-to-2 freeze out. So these two are very similar, and they both rely on the 3-to-2 freeze out. So now the interesting thing is this: can I have a 5-pion interaction that do the 3-to-2 freeze out, but I also have a vector Meson to do the resonant self-interaction? So the lattice result actually tells us yes, you can get both. So that's exactly what we do. So we grab one of these very clever model by Hitoshi and other people, and then all those things are specified. You have the Wezumino-Witten term, you have 3-to-2, you have these symmetric breaking, and then you have all the pion, you have all the pion interaction. So everything work out, you have a 3-to-2 self-interaction. Now you look at the lattice result that studies specifically this theory, and then you find out, so that people actually did a dark QC lattice study. You find out that, okay, I do have a vector resonance in a specific parameter space. The m pi over f pi is 1.9. And then I actually do have a resonance. So I could have a pi plus pi minus to v and go back to pi plus pi minus kind of story. So this also checked out. So it seems everything is fine, and we're having a very nice model. But there's one thing that failed us. That is the 4-pion interaction. Because once you specify all this stuff, you specify the 5-pion interaction and the vector resonance, you also specify your 4-pion interaction. And the 4-pion interaction is actually too large, and then this will be ruled out. So this is again provided by the constraint. So this ties back to what I say in the beginning, that the constraint is very important. This cluster constraint is very important, which I plotted here. It's easy to say. So this cluster constraint is very important because this cluster constraint in certain parameter space, you have to have 0.1 centimeter square over G kind of cross section. Of course, there's an uncertainty, but this will kill you once you have too large of a 4-pion interaction. So this can provide very meaningful probe for interesting model. And furthermore, one thing that we're planning to do right now, actually we're already working on, this is with Haibo and Manoj, is to have a velocity dependent constraint for different parameters and focusing on very small scale. And things here are very messy, but we're trying to get some kind of way to quantify things or things like that. Even though the uncertainty would be very large, still it's interesting to study this regime, because this regime can differentiate a lot of different models. And yeah, if there's more reference, please let me know. Thank you very much. And comments and suggestions are welcome. And thanks the organizer and all of you. Thank you.
Okay, thank you very much. So we have time for some questions. So maybe I will start with a little question. So you focus on resonances, but do you get similar effects with bound states?
I think so, yeah. I think resonance and bound state are kind of similar, but when we consider resonance, you can really think about you go through a actual particle, right? You can really think about that you have a resonance state. And bound state, there's a lot of study like Sommerfeld, kind of these kind of bound state, or other kind of bound states. So I think there is similarity between these two.
But it will also give you a feature in the velocity of elastic cross section.
Yeah, definitely. Yeah. So I think it's good to also consider bound states, and that will also give you a resonance. And I think Hitoshi actually have a paper classifying this, but they didn't do a very specific model. They didn't build a specific model, but they classify what's the difference and what's the similarity between bound state and resonance. Yeah.
Okay.
So I think that's interesting to do. Yeah.
I mean, if you have some nuclear physics in dark sector, you can have the analog of deuterium and deuterium, and
Yeah.
so. But I don't know if it was exactly if it makes it. I mean, for phenomenology, what you really want, if it makes a difference. I mean, for you, it seems important that you go on shell.
Yeah. I mean, it doesn't have to go on shell. You don't really have to. Even if you don't go on shell, you will also still have a kind of resonance. The behavior is slightly different, but you also have that. So that's something to consider for sure. The deuterium idea, we chat about this, we haven't really worked out the detail. But yeah, like dark deuterium or things like that could work. We just haven't explored it completely.
Okay.
But it's interesting, yeah. I think some people probably did it.
Yeah, you wrote a paper with Andrea Tesi.
I see. Sorry, I should take a look. Yeah, I think I probably.
Think we're not the only ones, probably.
Yeah. Yeah, I should take a look. Yeah, certainly.
So hello, can I ask a question?
Sure.
Okay, so my question is regarding that asymmetric dark matter. So your asymmetric dark matter is coming from the construction of the Lagrangian itself, because my question is this asymmetric dark matter coming dynamically? That means if you start from a symmetric initial condition, can you generate this asymmetric dark matter? So then would you get this 5 GeV mass?
Yeah, so I think that's the kind of UV model building that we can do. You can have like the cogenesis or things like that. We didn't really specify it because we didn't really worry about the very UV stuff, how you produce it. But I think it's kind of nature to write down something that you can generate. You can have a cogenesis, for example, mentioned by Evan, that things, for example, you can have heavy stuff decay to asymmetrically to both dark sector and standard model sector. And 5 GeV would be nature because the abundance of dark matter is 5 times more than the standard model particle. So that's why I say 5 GeV. But certainly when you build a specific model, it might not be 5, it might be slightly different. So it's interesting to really build a model. But that wasn't our focus in our paper. We just want to really have a resonance self-inverting dark matter, but it's certainly very interesting to also build a model for that.
Okay, thank you.
Thanks.
Any other questions? Okay, if not, we thank the speakers for the interesting talks, and we'll see you sometimes in the future.
Yeah, thank you very much. Thanks.
Bye-bye.